I wanted to do some more examples from chapter 23 to make sure that you've seen enough. I'm sorry I couldn't get a printout of these notes to you, but I just am doing this. I haven't done these examples before. I will, however, post a copy of the notes as well. If you have the potential to be able to print it out, that's great. Otherwise, at least you can just pull up these while you're doing your homework, although I hope you're watching the video because it helps. So problem number 9, these are all from chapter 23, so you could look up the page if you wanted to, but I have the problem right here. On problem 9, they actually give you the confidence interval, so you don't have to create anything. This is common on the AP exam, and I think perhaps even more common this year. So part A just says, explain carefully what the software output means. So you're just interpreting this, just like we've interpreted for proportions, except now make sure you're using the correct vocabulary. I am 95% confident that the true mean pulse rate of adults in the population is between 70.9 and 74.5 beats per minute. Don't forget to use units when they are applicable. Notice I didn't know what population we're talking about, so I just said in the population. Be careful that you don't say the mean pulse rate in the sample, because that would be incorrect. We know all of them are in the we know that the mean is within there. So you're talking about the true mean pulse rate in the population is what you're talking about when you interpret a confidence interval. Part B says, what's the margin of error for this interval? So you have to do a little bit of clever work here. Remember that they don't give us our sample mean, but the sample mean is right in the center. So what I did was you can see here, I added these two. I found that the average between 70.89 and 74.50. And I just added them up and divided by 2, and I got 72.69. That's the mean pulse rate for the sample. Then what I did is I just took I took the upper level and subtracted the sample mean, and I got 1.81. That's the margin of error. Okay, so you have to find the middle. Once you know what the middle is, you just have to know the distance between the middle and either one of the edges. That's your margin of error. Part C, if the researcher had calculated a 99% confidence interval, would the margin of error be larger or smaller? Remember that more confidence means you need and I don't know if I use that idea of a net. I know if I were in class I would, but more confidence would mean you need like a bigger net to capture the true mean, so it would have to be larger. Also remember, with a higher level of confidence, your T-star critical value is going to be bigger, and because it's bigger, it's going to make your interval larger. So the more confidence that you want to have that you capture the true proportion, or the true mean, not proportion this time, the more confidence you have, the larger your interval will be. On number 11, we're told, talking about body temperature, the researcher described in exercise 9 also measured the body temperatures of that randomly selected group of adults. The data he collected are summarized below. We wish to estimate the average or normal temperature among the adult populations. Part A asks us, are the necessary conditions for a T interval satisfied? So I went through those. First, in the problem, I'm told it's a random sample, so I wrote that down. Since it's random, each adult should be independent. We're told that n equals 52. Remember, if it's bigger than 40, that's big enough. So it's large enough, and also we were given a histogram, and it looks roughly normal, so we're good. And even though n is bigger than 40, they gave you the histogram. You should mention that as well. We also know that 52 is less than 10% of all adults. Again, I don't know the population it was coming from, so but I'm assuming that. Maybe it's all the adult population, but I don't really know that, if it's a particular town or where they drew the sample from. So because the conditions are met, I'm going to do a 1 sample T interval for the mean, because that's what they asked us about. So then in part B, they ask you to find a 98% confidence interval for the mean body temperature. Now, if you do it on your calculator, you're going to use the T interval, and you're just going to plug in the information. Notice my X bar came from up here. My standard deviation was right here, so I got that information from the chart to plug that in. N was 52, and it gave me my confidence interval. If you need to build it by hand, remember we talk about degrees of freedom. N is 52, so we have one less degree of freedom. So we have 51 degrees of freedom. That's not listed on your yellow sheet. So if you use your yellow sheet, you have to use the 50, the T star for 50. If you look that up on the sheet, and I know in the video you guys watched yesterday, I talked about that. So you're going to look up this value. And then I used that S and I used 52 and plugged it into the formula and got this. And you can see that it's basically, to 3 decimal places, it is the same. Then part C asks you to explain the meaning of that interval, so you are interpreting. I am 98% confident that the true mean body temperature of adults in the population is between 98.058 degrees and 98.512 degrees. I suppose I could have put an F there for Fahrenheit. Notice that this is exactly the same way you interpret a confidence interval for proportions, except we're talking about means instead. Part D says explain what 98% confidence means. Well, it means the same thing that it did for proportions, except I'm going to talk about means. So it says 98% confidence means in repeated sampling of size 52 from the population, 98% of the confidence intervals created will capture the true mean body temperature. So again, you should notice that the verbiage of this sounds so much like what we did with proportions. Part E, 98.6 degrees Fahrenheit is commonly assumed to be normal. Do these data suggest otherwise? Explain. Notice that 98.6 is above my entire interval. So this would suggest that the true mean body temperature is lower than 98.6 degrees. Okay, so that's all the parts you would include in a confidence interval. Oops, didn't mean to do that. Oops, okay, that was bad. Hold on. Okay. So still looking at the same kind of problem, would a 90% confidence interval be wider or narrower than the 98% confidence interval you calculated before? Explain. So a 90% confidence interval will be narrower than a 98%. And one reason you can think of the T critical value is smaller. So you're multiplying by a smaller number, which means you're going to create a smaller interval. So that is kind of an easy way to think about it. Part B, what are the advantages and disadvantages of the 98% confidence interval? Well, an advantage is we're more confident that we capture the true mean temperature because it's a higher confidence level. So we are more confident we capture the true mean. However, a disadvantage is our interval is wider, so we are less precise. So there we have an advantage and a disadvantage. And I wrote my sentence, and then I went back and realized I should really specify what do I mean by advantage and what do I mean by disadvantage. So I want to make sure I communicate that clearly. Part C, if we conduct further research, this time using a sample of 500 adults, how would you expect the 98% confidence interval to change? Well, with a larger sample size, we can create a narrower interval without decreasing our confidence level. Remember, we are dividing by the square root of n. So we're dividing by a larger number, which means our confidence interval will be smaller because our margin of error is smaller. But yet we didn't lose any confidence. So that is a good way to go. Part D, how large a sample would you need to estimate the mean body temperature to within 0.1 degrees with 98% confidence? So we want a margin of error of 0.1, which is what that means. So we take our critical value, and here's the problem. What we really would need to know is our T star critical value and times the 0.6824 over the square root of n equal to 0.1. But remember, this is n minus 1. Well, we can't solve for this because we don't know n, so we don't know what that critical value would be because we don't know n. We need to just have one variable we don't know, not two. So what we do instead is what you can do is use z star as an estimate. So if you look up z star with, for the 98% confidence interval, and that's what we use for the proportions on that last line on the T distribution chart, you'll see it's 2.326. Just use that instead. Then you're going to plug it in. I showed the work here. You can pause the video and kind of look through that if you want to see what I did. I'm not going to talk all the way through it, but when you do, you get 252 for your value. And remember, you always round up. And on this last problem, it's TV safety. The manufacturer of a metal stand for home TV sets must be sure that its product will not fail under the weight of the TV. Since some larger sets weigh nearly 300 pounds, the company's safety inspectors have set, that's not true anymore. TVs used to weigh a lot. The company's safety inspectors have set a standard of ensuring that the stands can support an average of over 500 pounds. Their inspectors regularly subject a random sample of the stands to increasing weight until they fail. They test the hypotheses, and they give you the hypotheses test using a level of significance of 0.0, alpha is 0.01. If the sample of stands fail to pass the safety test, the inspectors will not certify the product for sale to the general public. Okay, so I wrote out my H naught and my HA based on what they said. I wrote out words because it's helpful when you are doing the type 1 and type 2 error, which I noticed we had to do. So the null hypotheses would be to say that the TV stands can support 500 pounds. The alternative would be to say that they can support more than 500 pounds. And really embedded in the null is to say that it's like 500 or less, but our alternative is that it can support more than 500 pounds. Is this an upper tail or lower tail test? In the context of the problem, why do you think this is important? Upper tail because the manufacturer wants to be sure the TV stand is safe. For part B, explain what will happen if the inspectors commit a type 1 error. So remember, a type 1 error means the null hypothesis is true, but I accept the alternative. So, because I rejected H naught and accept the alternative. So the inspector certifies an unsafe product and consumers could be hurt. Okay, so that would be a bad thing, obviously. And then they ask you to interpret a type 2 error. And what that would mean is the inspector does not certify a product that is safe and the manufacturer loses money. So being able to interpret a type 1 and type 2 error, this is exactly the same thing that we did with proportions. So hopefully, I really hope that you see the similarities between inference for proportions and inference for means. Just make sure that you are using the correct vocabulary and that now you are talking about means. So hopefully that helps you for the homework problems that you are assigned.